The piezoelectric matrices and piezoelectric coefficients that we defined earlier and used earlier were all given in a so-called crystallographic coordinate system, where crystal axes are defined according to some principal axis of the crystal. It is, however, interesting to see how these matrices would look like in another coordinate system, and what is equivalent, how would how would piezoelectric coefficients, how would their values change if we rotate crystal, cut it under different angle, and so on. It turns out that this is of very great practical importance. Find out that the most performant crystals, rocks or ferroelectrics, have the largest piezoelectric coefficient, not along polarization, but some other direction. And for a quartz, for example, for timekeeping, the most stable piezoelectric property, such as resonance, is observed along angles, along directions that are not some of the principal crystallographic directions. This is the job that's in front of us in this section. How can we do this? How can we go from one coordinate system to another? Well, you know this from your physics and mechanical courses. You use Euler Angles to describe, to go from one coordinate system or another, or what is equivalent to rotate a body in the same coordinate system and look at it under a different angle. So the crystal can be the rotation can be described by Euler Angles, and I will use here X convention. There are other Y and Z and so on. You can find discussion on those different conventions in this website of Mathematica. In X convention, we have rotation around z-axis by angle phi, and then rotation by theta along new x-axis, and then rotation by psi around a new z-axis. This is psi, this is theta, and this is phi. Now, each of these rotations can be described by a matrix, and together these three rotations give Euler angles, give Euler matrix. The rotations have to be performed in a certain order: first D, then C, then B. The matrices are not commutative. The multiplication of matrices is not commutative, as you know, so that makes sense. And when we multiply all this in X convention, this is matrix of Euler rotation in terms of Euler angles in X convention. Should be careful. While description of rotation by Euler angles is unique, the definition of Euler angles is not unique. So one type is used in mechanics, another in quantum mechanics, one in aerospace engineering, and they will all give different A matrices. The final result is the same, but you cannot mix angles from different matrices, so you have to be careful and know exactly which Euler convention you are using. Now, how to make a transformation of piezoelectric coefficients from one system to another? We take values in crystallographic system, and we apply these matrices to get value at an arbitrary angle defined by phi, theta, and psi. This is valid only for tensors. when you express piezoelectric coefficient in a tensor form, so note here 3 indices. If you work with matrices, then different transformation rules apply, and you can find this in Nunnem's book. Also, we use here Einstein convention over summation over repeated indices, so we drop this sign sigma. So this and this is exactly the same. We simply drop sigma if indices are repeated. Also, transformations of the type inversion, which cannot be described by rotations, have to be added separately. So inversions such x, y, z into -x, -y, -z cannot be described by rotations, and this inversion has to be added separately. So let's try that. Let's apply inversion on a centrosymmetric crystal and show why in centrosymmetric crystals piezoelectric coefficients, piezoelectric effect must be absent, coefficient must be all 0. So inversion is given by this transformation, and we also need to consider two principles, Neumann principle and Curie's principle. And Neumann principle says that symmetry of any physical property of a crystal, such piezoelectricity, must include symmetry elements of the point group of the crystal. So if we work with the centrosymmetric crystals, which are invariant under inversion, then the piezoelectric coefficients must also be invariant under inversion. And the Curie principle, which we are not using this time, says when certain causes lead to certain effects, the symmetry elements of the causes should be observed in these effects. So if you apply electrical field to induce piezoelectric effect, then the piezoelectric effect, the strain, must include symmetry elements of the causes. And we will see that maybe later on. But let's see how this Neumann principle and inversion can tell us that centrosymmetric crystals cannot be piezoelectric. So we start with this is Euler matrix. This is inversion matrix. We multiply and we get this. And then we apply this on a crystal, on a piezoelectric coefficient in an arbitrary direction. And we get -1, -1, -1, give us minus that dijk in arbitrary direction must be equal to -ijk. In arbitrary direction when we make inversion, when we make inversion must be equal minus dijk, and according Neumann's principle, that has to be equal to itself. Under inversion in centrosymmetric materials, we repeat the crystal, and by Neumann's principle, we have to obtain the same piezoelectric coefficient. If something is equal to its negative, then it has to be 0. So we have a proof, a mathematical proof based on Neumann's principle and Euler transformation, that in centrosymmetric crystals, the piezoelectric coefficient has to be 0. Let's look now group 4mm, for which you know that we have these coefficients D31, D33, D24, D15, these are equal, so only 3 coefficients, and the rest of them are 0. Let's derive that somehow. Now we can do that just by looking at this structure, and we have already done it when we define different coefficients, but now we will do it in a mathematically rigorous way. So in a 4mm crystal, we have rotation around x3 axis by 90 degrees, and the crystal has to repeat itself. By Neumann principle, the piezoelectric coefficient, if you rotate crystal by 90 degrees, has to be exactly the same. So we put these angles into Euler matrix, we get this. So x will be transformed into y into minus x, and z or z remains unchanged. So let's look at D11 coefficient. And after expanding this using for matrix A elements, this matrix here, we do that, we obtain this is 0, this is 0, this is 1. We get that when we rotate crystal, D11 will transform into D22, but since it has to be equal to itself, if we rotate it by 90 degrees, we get that D22 must be equal to D11. And this is normal. We know that crystal is same, just as we look at it, is same along 1 and 2 axes, and it is normal that D22 and D11, or D22 and D11 must be the same. D22 would be in matrix form, D11 in matrix form. Now, let's apply mirror symmetry element, which is perpendicular to M axis, like this. And that means that X remains unchanged, Z or Z remains unchanged, and y goes into minus y. So let's see how D22 will transform. We get that D22 will go, after we apply this mirror plane, into minus D22. And by Neumann's principle, it has to be equal to D22 to itself. It shouldn't change. If something is equal to itself minus, then it has to be 0. And D22 is 0. And since we previously showed that D11 is equal to D22, that also has to be 0. So this is D11 and this is D22. And we can do that for all other elements. By doing this, we can show that D15 and D24 must be equal, and that D31 is equal to D32, and that all other elements must be different from 0. Now, let's take one particular crystal, barium titanate. It's a 4mm crystal, and let's see how it looks like, how it changes in the space under different angles away from polarization. So this would be theta equal to 0, and this would be some angle, I don't know, 30 degrees or so. So we will go from 0 to 90 degrees in theta. All other angles are equal to 0. We are only rotating around x-axis by angle theta, phi 0 and psi 0. So we get, if we apply Euler Matrix, and you can try to do that, this is a relatively easy calculation for 4mm, we get that D33 under at an arbitrary angle theta is equal to this. D33, D31, and D15 are values of piezoelectric coefficients in crystallographic system. And now we take these values at two different temperatures, at 360 kelvins and 290 kelvins, and we calculate how D33 changes in space. And we find out that we get this elliptical shape or ellipsoidal shape at 360 degrees, but changes in this shape when we go to 290 degrees. Actually, piezoelectric coefficient becomes larger at some angle approximately 54 degrees away from the polar axis. Remember, in tetragonal material, this is polarization here. So why there is this change and why coefficient becomes larger along some non-polar direction. Well, let's consider this as it will become very important for us later on. So if you look at piezoelectric coefficients in tetragonal phase, here is orthorhombic, here is cubic phase. So here is cubic, here is tetragonal, and we are looking at piezoelectric coefficient in the tetragonal phase. And we will focus on D15 and D33, and we see the D31 does exactly the same thing as D33, except that it is negative while D33 is positive. So we can forget about D31 for the moment and just look at D33 and D15, which have different trends with the temperature. Why is that so? Well, we can explain it by looking direction of polarization in these structures. So in cubic structure, polarization is equal to 0. There is no polarization. In tetragonal phase, polarization is polarization is along P3 axis and is along 0, 0, 1 axis, P3, and in orthorhombic polarization is along 0, 1, 1 or 1, 0, 1 and so on, these equivalent directions. So as we are heating material toward cubic phase, polarization will do something like this, and then it's 0. And when we go to orthorhombic phase, polarization goes like this. So cubic, tetragonal, and orthorhombic. Okay, polarization is like this. Here it's 0, and here will be under under an angle. Now, let's see what piezoelectric coefficients mean. We have polarization, D33, sigma 3, D33 is by definition delta. It explains, it explains how polarization changes with respect to pressure which is applied along faces which are perpendicular to the 3 axis. And D15 tell us how P1 changes if we apply pressure along this face which is perpendicular to X3. So piezoelectric coefficient always describes changes in polarization. So why should this lead to this temperature dependence? Well, the reason is the following. Let's look first at tetragonal structure, and we and going up with the temperature and observing D33. Now, what is going to happen to polarization along 3 direction as we increase the temperature? Eventually, once we go to phase transition, it will disappear. The polarization will become 0. And this means that we have here pre-transitional behavior. The coefficient feels what will happen with the polarization even before polarization becomes 0. The coefficient feels that polarization must become soft to changes along X3 direction, because it will go from here into 0. And the crystal feels that even before that happens. We will be able to describe this more rigorously with the free energy later on, but just to give you an intuitive view of what is happening. So as we are increasing the temperature, the polarization becomes smaller and smaller, and its susceptibility to changes in that direction becomes bigger and bigger as we are approaching phase transition, and therefore D33 will increase with increasing temperature. And for D15, it is opposite. We start polarization with X3, and in orthorhombic phase, we will have this component along X3, but we will develop a new component, a crystal will develop a new component along axis X1. So polarization P1 is 0 here, but will develop later on. So as we are cooling crystal toward the phase transition, whenever you are approaching the phase transition, the crystal becomes susceptible to the changes that will happen once you go over the transition point. So making what shear coefficient is describing. It is describing rotation of polarization. It is describing rotation of the polarization away from the normal direction, and when polarization rotates, it develops this component P1, and that component will eventually be very large, and therefore crystal feels that as it is in tetragonal phase, anticipates that phase transition, and therefore gives a large D15 coefficient. I should actually write here, it would be more correct, delta P1 and not P1, because we don't have polarization in that direction in tetragonal phase. However, we develop it when we apply pressure, shear pressure in this direction. Then remember definition of shear coefficient, it will rotate polarization, and that will develop this component delta P1. And we are looking how that delta P1 is changing as we are changing the temperature and applying pressure sigma 5, which we have to apply in order to measure D15. We will repeat this later on when we discuss other crystals in a different context. But I urge you to think about this and talk to me if you have any questions about that. Okay, so remember, it is correct to write it like this rather than P1, which can be confusing. Now we will just quickly look at the D33 coefficient in a rhomboidal 3M symmetry. That's the symmetry that gives the largest piezoelectric coefficients that we know and that are of practical interest. So this is the polarization in this crystal. It's along 1, 1, 1 direction. And it turns out that the largest piezoelectric coefficient, this is piezoelectric surface, as a function of space, that the largest piezoelectric coefficient is under an angle of about 54 degrees, which is 0, 0, 1 direction in a rhomboidal, in a pseudo-cubic representation. And the D33 as a function of, when you look at this rotation, you actually have to also take angle phi, as opposed to barium titanate, where material is same regardless of which angle phi you take. Here it changes. It has this 3 symmetry that you see. If you look along this, you see a threefold symmetry which repeats itself. So piezoelectric coefficient is equal here, here, and here, and that's angle of 120 degrees. So this looks much more complex. than for tetragonal symmetry. So if you want to play with these things, it's best to play with tetragonal symmetry, which is more straight forward.